now we are moving to the third and final contributed talk of today. Right now, we have the pleasure of listening to Monte Cairns from the University of Cambridge, whose talk titled Nuclear Charge and the Causal Powers of the Elements, Electronegativity as a New Problem for Reductionists and a New Case for Emergence. So, Monse, you have 20 minutes for your presentation. When you have spoken for 10 minutes, I will interrupt you to let you know that you have 10 minutes more. So, the floor is yours.
Brilliant, thank you. If you can hear me and you can see everything properly.
Yes.
Wonderful. Today I'm going to talk about some research I've been doing adapted from my master's dissertation on the chemical concept of electronegativity in relation to some issues regarding ontological reductionism and emergentism. I am pretty new to the discipline, so if I make errors or if you have thoughts, I would enjoy hearing about them. Electronegativity is a central concept in contemporary chemical practice, and it's typically defined along the lines of the propensity of a given atom to donate or receive electrons under bonding conditions. There's been some philosophical work done on it, particularly in the past 5 or so years, which has tended to focus on different measures of electronegativity connoting contradictory ontologies. And today, what I'm hoping to indicate is that the broad concept of electronegativity has some interesting ramifications for reductionism. And in particular, I think that the plausibility of the emergence view, which is usually reserved for higher level chemical entities, such as molecules and compounds and so on, can perhaps be extended to chemical elements as probably the lowest level of chemical entities on the basis of electronegativity. Now, terms like emergence and in particular reductionism carry some pretty enormous philosophical baggage, which I'm mostly hoping to avoid today, but I do need to clarify what exactly I mean. I'm pretty much taking my cue from Robin Hendry, who is, to my knowledge, the most prominent proponent of the plausibility of emergence for some chemical entities. And as per Hendry, the reductionist thinks that the properties of higher level chemical entities are no more than their physical bases, because the causal powers they confer are a subset of those conferred by their physical bases. The emergentist sees them as distinct and non-reducible just because the causal powers they confer are not exhausted by those conferred by their physical bases. So for a chemical entity to be reducible, its causal powers have to be a subset of its lower level constituents. Now, clearly this is an ontological framing of the issue, which is fitting considering including emergence, but as Hendry himself is perfectly aware, an ontological dispute like this is going to be evidentially underdetermined, and any evidence you can provide will regard epistemological reduction, by which I mean, for current purposes, the explanation of some aspect of chemical theory in exclusive reference to physical theory. Since we obviously want philosophical debates of this kind to remain as grounded as possible, then following Hendry, I think we should accept that successful epistemological reduction is grounds to believe in ontological reductionism, whereas if there is no epistemological reduction for the causal powers of some given chemical entity, I suggest we ought to accept that emergence is plausible. I'm going to emphasize causal explanation throughout as a sort of middle ground, an epistemic accomplishment with at least intuitively ontological implications. Now, with a bit of philosophical preamble out of the way, I think it's safe to say that the standard view in philosophy of chemistry is that reductionism for higher level chemical entities like molecules and compounds is not evidentially supported. The evidence against reductionism for these evidences, that's most regularly trotted out are chemical isomers. So if we take ethanol and methoxymethane, they share a chemical formula, but they have very different chemical properties, including ethanol's much higher boiling point, for instance. These obviously distinct substances cannot be meaningfully distinguished by purely physical, by which I really mean quantum mechanical descriptions, since they feature the same fundamental constituents and so have equivalent Hamiltonians, essentially. We can meaningfully describe and differentiate between isomers in the language of quantum mechanics, but this requires essentially sort of bolting on chemical theory in the form of molecular configurations by way of the Born-Oppenheimer approximation and so on and so forth. What isomers do is demonstrate that a causal explanation from the fundamental constituents of a molecule to the properties of that molecule or substance is not currently available. And as such, it's been argued, it's plausible to infer emergence, or just as plausible as it is to infer the reducibility of molecules. but this is limited to molecules. And I came to these issues thinking about natural kinds. Chemical elements are obviously considered some of the best evidence for the existence of essential natural kinds. But I think if we keep in mind that arguments for emergence are restricted to molecules and other higher entities, I think some natural kind talk about elements has a pretty clear reductionist bent. So for instance, we have these quotes from Hendry that the presence of an element in a compound explains the chemical properties of the compound. It is nuclear charge that overwhelmingly determines the chemical behavior of both elements and compounds by the electronic structure of free and bound atoms. Now, this is formulated in the context of natural kind disputes, and I'm not arguing that Hendry is committed to reductionism about chemical elements, but I hope you'll agree that an implication of this claim is that the physical bases of atoms, and in particular, a number of protons in a nucleus, confer the causal powers of atomic species. And I think that this sort of interpretation is strengthened by this other quote from Hendry regarding the existence of super heavy elements. It's a more recent paper, that an object of a particular kind can be said to exist only if it is in principle possible for it to exert the causal powers that are characteristic of members of that kind. For an element to exist requires electronic structure, and the chemistry that structure makes possible. Again, this looks like an at least implicit acknowledgement that electronic structure confers the causal powers of elemental kinds. That's decided to quit working. I also don't think that this sort of at least implicit reductionism is limited to philosophical views on the nature of elements. We look at IUPAC's criterion for the discovery of a new element. It reads, as the discovery of a chemical element is the experimental demonstration of the existence of a nuclide with an atomic number not identified before, existing for at least 10 to the power of minus 14 seconds. This lifespan is chosen as a reasonable estimate of the time it takes for a nucleus to acquire its outer electrons. It is not considered self-evident that talking about an element makes sense if no outer electrons, bearers of the chemical properties, are present. This, again, seems, at least to me, to imply that the causal powers of atomic species are a subset of the causal powers of their physical bases. And all this sort of led me to wonder if, in fact, it seems well substantiated that atomic species are reducible. If we are to wholeheartedly accept their reducibility, then I think we ought to expect that there are available causal explanations from the physical bases of atoms to the causal powers with which we associate them. Throughout the literature, at least that which I've come across, the assumption seems to be that because valence can be explained via electronic structure, and because electronic structure is determined by nuclear charge, then atomic species are reducible. But as you've probably guessed, I don't think that electronic structure or any of the empirically demonstrable causal powers of an atom's fundamental constituents provide adequate causal explanation to justify being reductionist about atomic species. So I think this point can be pretty neatly demonstrated just by considering how chemists explain the distinct boiling points of ethanol and methoxymethane. Although these explanations are complex, it seems to me, at least, that the crucial means by which these explanations are made is via bond polarity. So in ethanol, but not in methoxymethane, an atom of hydrogen is in a polar covalent bond with oxygen. This OH group leaves the hydrogen atom with a positive charge, which permits intermolecular H bonding in a measure of ethanol, and therefore it's significantly higher boiling point on the basis that there are more bonds to break in ethanol than there is in its isomer. But if nuclear charge or electronic structure overwhelmingly determine the properties of compounds, as Hendry claimed in the proceeding, then it seems reasonable to propose that they ought therefore to explain bond polarity. But this isn't really the case to my knowledge, and bond polarity cannot be explained in reference to the fundamental constituents of atoms. Of course, electronic structure is necessary for the formation of any bonds at all, but the distinct bond polarities in molecules of ethanol and methoxymethane are underdetermined by it, so that there can't be any causal explanation from electronic structure to bond polarity and thus their respective boiling points. Instead, the necessity of electronic structure just establishes what I'll call an existential dependence for chemical properties, as in on electronic structure. An obvious rejoinder to what I'm getting at here is that I'm developing the point in direct reference to isomers, which are already acknowledged to have potentially emergent properties, but I'm using isomers to form a rhetorically useful contrast in demonstrating underdetermination, and there's nothing special to their status of isomers for this lack of explanation from physical bases to the properties of compounds. So for instance, there are no known isomers of water, but its anomalously high boiling point in comparison to similar molecules is explained by intermolecular H bonding in much the same way as ethanol's is. As I've framed it, there's an at least implicit reductionism extant in philosophical and scientific literature on the nature of chemical elements. This claims that the causal powers of atomic species are exhausted by those conferred by their physical bases. If this is to be wholeheartedly accepted, then we ought to expect that causal explanations are available from fundamental particles to the causal powers of elements. But there is no causal explanation available from the constituent particles of oxygen and hydrogen to the boiling point of water. The way I see it, we have two options on this basis. We can accept that there isn't compelling evidence for full-on ontological reductionism about chemical elements, or we can accept that oxygen and hydrogen play no causal role in the boiling point of water.
Excuse me, Monty, 10 minutes more.
Brilliant. But by accepting the second option, we would be sort of abandoning the view that the presence of an element in a compound explains its properties. And so I think there's good reason to hold that reductionism about chemical elements is evidentially unsupported. But here we find ourselves at a bit of an impasse, because even lacking evidential recourse, the committed reductionists can just assert their ontology, and it isn't possible to provide decisive evidence against ontological reductionism. Indeed, the classic reductionist move when faced with issues like this is just to claim that were physics sufficiently elaborated, it would provide any missing explanations pointed out by the anti-reductionist. But I want to avoid allowing the debate to devolve into the assertion and reassertion of ontologies. And as such, I think the thing to do is to assess the plausibility of the claim that physics could provide explanations for the causal powers of atomic species that I'm claiming it currently doesn't. And in so doing, I'm going to discuss electronegativity. Now, electronegativity is typically defined as the relative propensity of a given atom to donate or receive electrons under bonding conditions. This propensity is represented by discrete values assigned to discrete elements normalized to hydrogen. To my eyes, it is electronegativity that is the crucial missing piece for explaining bond polarity in reference to a molecule's atomic constituents. For instance, oxygen is significantly more electronegative than hydrogen. Therefore, in an ethanol molecule, the atom of hydrogen bonded with oxygen becomes positively charged because of unequal electron sharing between the two. More generally, electronegativity is used to predict and explain the formation of, for instance, metallic covalent and ionic bonds, which in turn determine many macroscopic qualities of substances such as hardness, brittleness, melting point, and so on. As stated in a recent paper presenting a new electronegativity scale, it is one of the most important elemental descriptors, not only because it measures the propensity of atoms to attract electrons, but because it has been productively employed on countless occasions to guide molecular and material design. And all of this might look quite promising for the reductionist on the basis that if electronegativity could be explained in reference to an atom's fundamental constituents, then my critique thus far would be void. But I don't think we should be too hasty about that. And I actually think looking into electronegativity probably poses a more significant issue for reductionism. To begin with, huge numbers of quantitative measures of electronegativity have been developed, as partially indicated in this quote I have up here from Mark Leach. Moreover, new electronegativity scales with new methods of measurement are regularly proposed. And to my knowledge, there is no measure of electronegativity that is not relative. There's no direct measure that corresponds to a physical property. They pretty much all rely on relational comparisons, at least between two physical states. And as you can see here, the various measures of electronegativity only approximately cohere. So in this table, I have some results for a few elements from some of the more prominent electronegativity scales. I have max deviation in the bottom row. And as you can see, it gives the obvious impression of clustering. The deviations are small, but the combination of a multitude of unrelated measurement methods and inconsistent results leaves us with no clear impression of what electronegativity is beyond the highly abstracted definition I've given. And of course, relative propensity of an atom to attract electrons is not a physically observable property. The problem is only made worse in that various measures of electronegativity appear to connote incompatible ontologies. I mentioned, in particular, the tension is between thermochemical measures and atomic or spectroscopic measures. The problem is essentially that thermochemical methods take electronegativity values from the dissolution of bonds in molecular context, whereas atomic methods derive values from the characteristics of atoms in isolation. This has been taken as evidence for a sort of alive and well ontological incompatibility in contemporary chemistry, which I think is a bit of a mistake as regards how chemists think about electronegativity. I think it's wrong to think that there's a molecular relational electronegativity and an atomic intrinsic electronegativity alive within contemporary chemistry. The scientific literature reliably refers to it as a descriptor or property of atoms in isolation. Pauling himself understood electronegativity as such, agreeing with Mulliken's view, who I have listed there. But generally speaking, the operational problem remains that it's entirely unclear what electronegativity is in physical terms. That being said, its huge epistemic utility, and in particular, its potential codifying role as a sometimes been called a third dimension of the periodic table, has led to some proponents for understanding electronegativity as a definite atomic property. Mark Leach has proposed that we identify electronegativity as a single dimensionless number for each element. But the problem with this approach, lacking a physical basis for the property, is that different electronegativity scales have different epistemic utilities. For instance, of those recent scales I indicated a moment ago, one was developed for the specific purpose of predicting overall molecular charge shifts during chemical reactions, another for predicting bond lengths in specific molecular species. They both serve their intended purpose with greater efficiency than other scales, yet are less efficient for other purposes. Molecular context can also play a role in the usefulness of a scale, particularly regarding transition metals. The function of various electronegativity scales depends upon the number of bonds a given atom is engaged in, as well as if these are bonds with other metals or non-metals. So the problem for Leach is just that having a multitude of scales is best for epistemic utility. There's also the chemist Leland Allen, who has argued that a quantum mechanical description of electronegativity can be had by defining it as a per electron energy of valence electrons in s&p orbitals. But it's of limited utility, and more importantly, framing it as a quantum mechanical description is inaccurate, since orbital positioning must be bolted on in much the same way as molecular configuration gets bolted on when producing molecular Hamiltonians for isomers. I mean, configurational Hamiltonians. So where does this leave reductionism? Despite the best efforts of Allen, electronegativity has no known physical basis, and no causal explanation for it can be had from physical theory or fundamental particles. Moreover, establishing a correct electronegativity value for any element is preempted because various scales provide distinct, contextually dependent epistemic utilities. The various epistemic utilities of electronegativity make it indispensable for contemporary chemical practice, but it's unclear how plausible it is that physical theory could encompass all of this in reference only to fundamental particles in interaction with only a few fundamental forces. A common response to all this is to deny that it exists as a natural property. This may well be the case, but regardless of the actual ontological status of electronegativity, I think that the concept poses a pretty serious problem for reductionism about atomic species. Electronegativity is typically taken for granted as a descriptor of atoms in isolation within the scientific community. It provides a crucial basis by which chemists explain and predict the properties of substances in reference to their elemental constituents. And if we want to maintain that both the presence of an element in a compound helps to explain the properties of that compound, and that the causal powers of elements are exhausted by their physical bases, then whether or not electronegativity refers all its various and contextually dependent epistemic utilities will have to be explained in reference solely to the constituent fundamental particles of atoms. But I think given the strikingly disunified status of electronegativity as it is presently employed in contemporary chemistry, the availability of such an explanation does not look self-evident or plausible. Given that electronegativity is a crucial means by which chemists explain the properties of compounds in reference to atomic constituents, this would appear to render emergence about chemical elements as plausible as ontological reductionism about them. Now, I don't want to make a positive argument for emergence, but there are minor conceptual advantages to taking up the view. For instance, if we accept that electronegativity is an emergent property of atoms, properties of atoms, we can provide a satisfying causal explanation from the properties of oxygen and hydrogen to the boiling point of water. whereas under reductionism, an equivalent explanation would necessitate that explanation of electronegativity or electronegativities in exclusive reference to fundamental particles, which, as I've said, I'm not convinced is plausible. And that is me done.
Thank you, Monty. So we have only 5 minutes for questions and answers. So please be brief and concise with your participations. Anybody has a question? Okay, Aaron, please.
Am I audible?
Yes, we hear you.
Okay, right. I don't know if this is a helpful question, but I wonder if you've heard about or thought about the varieties of emergence that have been produced by human engineers in the last half century or more in connection with the new and enormously varied and increasingly varied uses of computation. I've mentioned this in previous occasions. So we have things like Zoom meetings, which in some sense are fully implemented in physical mechanisms, but the relationship between anything that you'll read in a textbook of physics or chemistry or electronics, whatever, and the properties of a Zoom meeting are extremely obscure, and you have to do a lot of study of current computer systems engineering in order to understand it. And that's just one example. Text processors, and many uses of the internet, and text editors, even on a simpler example. Anyway, the question is, have you thought about those as examples of emergence and whether they might give us any clues as to ways of thinking about emergence in biology?
No, I haven't. And it may well be that I need to do a lot more learning before I'm able to realistically comment on that sort of thing. I suppose I would say if I'm targeting chemical elements as plausibly emergent, that's on a much more fundamental level than we might be dealing with in terms of Zoom calls or even biological kinds. If I'm right, which I may well not be, it would have perhaps necessary implications for things like reductionism in biology, regardless of whether it was explicitly addressed to them.
Well,
but
just
that being said, I don't really know enough about these
a
things.
very brief, very personal comment. I've been thinking a lot about how processing eggs can turn a collection of kinds of goo into chickens, alligators, turtles, and various other things, which come out of the egg and also can then do things like feeding themselves, following the mothers and other things without any learning required. And it seems to me that hardly anybody is thinking about those processes, and perhaps some of the things that you've been talking about and we've been talking about might be very useful in going back to understanding how a lot of very familiar biology that is mostly, whose complexity is mostly ignored, how that familiar biology actually works.
Yes, absolutely.
Thank you. So the last question is for Pedro. Please. Pedro, you are muting.
Okay, a quick question, okay? Why do you think that contemporary chemists tend to think of electronegativity as an individual property of isolated atoms? You have any source? Have you taken that impression from your contact with other chemists, or?
So I'm basing that largely off of how it is discussed in scientific literature on the topic. Of course, as we know, chemists are often pretty disinterested in these sorts of questions, so it may just be a casual use of language without particular significance.
Well, I don't agree with that. I mean, I'm a chemist myself, and I have never got the impression that for chemists, electronegativity is an individual property of isolated atoms. I have always thought of electronegativity as a property of atoms in molecules. So a relational property.
Sorry, well, I may well just have gotten the wrong end of the stick with that. It is certainly discussed in specifically what I've been looking at is the production of new electronegativity scales. They talk about it as a property of atoms. How
elements, not atoms. I mean, which is the distinction is subtle but important. Okay. Well, I mean, it's just a comment. Okay.
That is a good point, actually. I could potentially have done with some more thinking in that direction.
Okay. Thank you.
Thank you.
Thank you, Monty, and the participants.